Okay, so the next topic is droplet evaporation and combustion. So we will consider an isolated droplet. Okay, so isolated droplet like this of radius at any time instant, its radius is Rs, and we will consider only the spherical coordinate. Spherical symmetric coordinate is only one dimension. So radius is the only coordinate variable in this. Okay, so if you see at any radius, the profiles will be the same. So it's spherically symmetric basically. So isolated droplet, and in a stagnant gas. Okay. So we have already seen the mass transfer when we did the mass transfer topics. We saw the evaporation features of this using the Fick's law. So we will touch upon some of the aspects here and move on to the droplet combustion. Okay. So now the basic assumptions in this what we have seen already are we can see that the evaporation process is quasi steady. That means at any time instant, the rate at which the droplet evaporates will be the same. So, for example, the radius may vary due to the evaporation, the mass going out from the liquid to the vapor, the radius can shrink, but the rate at which the evaporation takes place will be steady. So, at any instant we can find the evaporation rate, and that will be constant. The second one is the liquid temperature is uniform. So, in this droplet evaporation we will add this, where the already a wet bulb temperature has been attained. Okay. So, basically what happens, I will illustrate here. So, when you try to draw the d square versus t, in any realistic environment, you can see that there will be, so let us say we will also normalize this by the initial droplet diameter d naught and square it. Okay. So, d naught is the initial droplet diameter. So, when I draw the curve of a d square by d naught square versus time, so this will be 1. So, from this you can see that the initially what happens, normally the droplet will the diameter will increase, reach a maximum, and then it decreases, then you will get through what is called a constant evaporation regime, and towards the end again there will be some non-linearity again, non-linearity. Okay. So, you can see that this is the time period, the evaporation rate will be steady. So, the total time period is this. So, this is the total droplet time period, that is Td, out of which the major part, so I will say Ts, that is steady evaporation is found for this time period. So, initially there will be a increase in diameter due to what is called volumetric expansion. So, after volumetric expansion, the droplet diameter will reach the maximum value. Then, so this phase basically where the evaporation starts, and this is actually non-linear evaporation will take place. So, non-linear evaporation phase. So, volumetric expansion phase, where from the initial droplet diameter, the droplet diameter increases to a maximum value. After that, there is a non-linear evaporation state. Then, if you see Ts, this is the steady evaporation regime. So, this is the steady evaporation regime. And then after that, slight non-linearity will come towards the end. So, you can see that this Ts by T, the total droplet lifetime Td will be 80 to 90%. So, we can say that Ts by Td will be 0.8 to 0.85 or 0.9 even. Okay. So, that is why we concentrate on the evaporation constant, which is constant in nature. So, this assumption of quasi steady is valid. Only very little time in the front and very little time towards the end, we have some non-linearity where the steady state will not be there, but major portion 80 to 85% of the droplet lifetime you will have a steady evaporation phase in most of the cases, okay, not in all cases, in most of the cases. So, this type of steady evaporation is very much helpful for us. So, in this the liquid temperature will reach the wet bulb condition, that means surface temperature has reached a constant value of Ts, and here the internal temperature also has become a uniform temperature. So, that is assumed. Then liquid vapor equilibrium or vapor liquid equilibrium at any point in the surface, that is also achieved. That means there is a definite Ts and the saturation pressure for this Ts corresponding to this Ts prevails. So, that is also that. So, equilibrium vaporization occurs. Property being constant is the assumption what we have to make, because to reduce the complexity of the problem. So, all properties are constant. So, this particular analysis will be helpful. We are going to do this for the droplet combustion also. So, the vaporization we can see that the spherically symmetric. So, whenever vaporization takes place, it is only in r coordinate, the variations are in. So, for example, from the surface of the droplet where the mass fraction of the fuel is YFS, this decreases towards the ambient like this, okay, to a very low value when you go far off radius, this radial distance. Similarly, you can see that the temperature at the ambient is T infinity, which is higher, and we can see that there will be a temperature which is going to vary like this, and this will be the surface temperature Ts. So, these variations are only in radial direction. In any theta and phi in the spherical coordinate system, or theta and phi, in any theta and phi you will have only variations in the, or the variation in the r will be the same for any theta and phi. So, this is the spherical symmetric coordinate what we are going to consider for our problem, which we have already seen for the mass transfer analysis. So, we will just recap that. So, steady evaporation using the mass transfer. Here we have used the mass conservation, which is nothing but a fixed law. So, fixed law is written like this. Again we can see that the droplet, the ambient gas. So, this is say droplet as a liquid A and ambient gas is B. So, B does not dissolve in A, liquid A. So, the gas B, okay. So, this is gas and this is liquid. So, under this assumption the net flux of B here will be 0, okay. Net flux of B will be 0 and only B diffuses as the A vapor. So, the total mass flux will be only that of the fuel, here A or fuel F, whatever we can say. So, the net flux is of that of fuel will be here, again you can see this, this will be YA, YF, okay. So, rho F, VF, YF minus rho DFA. So, when you write this fixed law, okay, this is nothing but mass flux at the surface of the fuel equal to mass flux of the fuel, that is total mass flux, which is equal to the mass flux of fuel. Here the total mass flux will be equal to the mass flux of the fuel alone into YF minus this, the diffusion term rho DF A. A is the ambient fluid or ambient gas. So, DYF in the radial coordinate only normal derivative, the ordinary derivative is used. So, using this we can bring this to the left side. So, 1 rho F VF into 1 minus YF will be equal to the right hand side is minus rho DFA and the gradient. So, this flux, mass flux, the total mass flux will be written in terms of the gradient of the mass fraction. So, if you apply this to the surface, you will know the mass flux. So, now this is the equation which is just got by the mass conservation, and by integrating this you get the profile of the mass fraction. The profile of the mass fraction is got. Okay. So, here when integrate this and apply the boundary condition. So, at the surface when r equal to rs, yf will be equal to yfs, and so this is the first boundary condition, and second boundary condition is as r tends to infinity. So, it may not be infinity, it may be a large value of r, then we can see yf tends to yf infinity. So, this can be taken as 0 at a large r radius, this can be taken as 0. So, when you apply these boundary conditions, we have already seen this, when you apply these boundary conditions to this, this is the governing equation, and integrate this, then you get the profile of yf at any radial location r. Okay. Profile of yf at any radial location r is given by this. So, you can see this it is given by 1 minus yfs, that is the value at the surface, into exponent of minus m. Please understand that this is constant. So, this will be equal to constant. So, that comes out here. So, once you know the mass burning rate or evaporation rate, you can calculate YFR or vice versa. So, when you do this, so this is the equation you get. So, 4 pi rho dFB into R, similarly exponent of this at Rs. So, when I apply this boundary condition, you get this one of the boundary conditions, that is we apply this boundary condition here. So, first you integrate this equation, the flux, the first order derivative, you integrate this once and apply one of the boundary conditions, you get this profile. Then what you do is you apply the second boundary condition, and so when you apply this condition r tending to infinity, yf equal to yf infinity, and that can be taken as 0, then you will get this mass burning rate. Okay. So, the procedure what we saw already was you apply the Fick's law, understand that the gas B or the ambient fluid will not dissolve into the liquid droplet, and the total flux will be equal to the mass of the fuel alone. So, using this writing Fick's law like this, you can evaluate the mass flux as a function of the derivative of the mass fraction of the fuel, and once you do this, then integrate this with two boundary conditions. Apply one boundary condition to get the profile, then using the profile apply the second boundary condition to get the mass evaporation rate itself. So, when we do that, you get the mass evaporation rate, in which there is a natural logarithm term, and this term you write as 1 plus by. So, 1 plus by equal to 1 minus yf infinity divided by 1 minus yfs. So, that means by will be the Spaulding's transfer number. So, that will be written as yfs minus yf infinity divided by 1 minus yfs. So, this is the Spaulding's transfer number. So, we have seen this. So, this equation is called equation A. So, the mass evaporation rate got by analyzing the steady evaporation problem only using the mass conservation, you get an equation for the mass evaporation rate m dot, which is given as 4 pi rs rho dFA into natural logarithm of 1 plus by, where by is the Spaulding transfer number given as yfs minus yf infinity divided by 1 minus yfs. So, this is the equation A, which is got from the mass transfer analysis, which you have already seen in the mass transfer basics. Now, let us try to do the problem using heat transfer. Okay. So, you know that there is a droplet, and droplet has surface temperature is Ts and ambient temperature is T infinity. Now, T infinity is greater than the Ts. So, initially you can see that the temperature of the droplet may be at say T0, and this T0 first will be heated up to a equilibrium temperature. So, this surface temperature Ts is the equilibrium surface temperature or the wet bulb temperature. Okay, now, since Ts is say T infinity is greater than Ts, here the heat is added from the ambient to the droplet in order to increase the temperature from this to this. Once the equilibrium temperature is attained, then steady vaporization occurs. Okay. Now, So, let us try to obtain the mass burning rate using the energy equation now. So, energy balance is written like this. So, you can see that m. So, this is nothing but rho v m, this flux m dot double dash is the flux rho v into Cp into dt by dr. So, convective term. So, this is the convective term equal to the diffusion term. That is the heat conduction. So, Fourier heat conduction. So, this lambda is the thermal conductivity. Okay, now you can see this is the energy balance what we have. There is no source term or any reaction, chemical reaction, anything. So, this is what we have. In fact, for the diffusion flame, we do not need to consider the chemical reaction at all. So, now the flux you can multiply by 4 pi r square, the surface area, in order to get the flow rate, that is kg per second. So, this is actually kg per meter square second multiplied by the surface area, that is in meter square. You get this m dot into Cpg into, so 4 pi r square, so multiply and divide by 4 pi. So, you get, and properties are constant. So, thermal conductivity, which is in the right hand side previously, now it moved down here, and you get this equation. So, now you have a second order equation in temperature, and we know that the properties are taken constant. So, Cpg, lambda are taken as constants here, and the mass flow rate is written here, m dot, that is the evaporation rate. Okay. So, that is happening only at the interface. Okay. Now, as I told you, Cpg is the gas phase specific heat, and lambda is the thermal conductivity of the vapor mixture, gas thermal conductivity. So, now there are boundary conditions at two locations, as we saw in the mass transfer. At the interface, R equal to Rs, that is the equilibrium temperature prevailing Ts, T equal to Ts. Similarly, when R tends to infinity or large radius, you get the ambient temperature T infinity. So, these are the boundary conditions, and we will try to solve this problem. So, we can see that if the properties are constant, so we know that the mass evaporation rate under steady condition, steady evaporation, mass evaporation rate m dot equal to constant. So, m dot is constant. So, m dot is constant, Cpg is constant, lambda is constant. So, this is a constant basically. So, the integration of this equation is quite possible now. So, because we assume that the properties are constant. Okay. So, either the properties are held constant or they have to be calculated at the appropriate average temperatures. So, when you do that, then we can get proper values for the mass evaporation rate. So, this equation is a second order equation which can be integrated twice and apply the boundary condition to get the values. Okay. So, that is what we are going to do next. So, as I told you, all the properties are assumed to be constant, and I can integrate the energy balance equation 2 times and apply the boundary conditions what we have solved at T at R equal to Rs equal to Ts, and T as R tends to infinity will be equal to T infinity. When you apply that, you get this, say first of all you can get a profile for temperature. Okay, a radial profile, and you can see that T infinity minus Ts, which is the driving force for us, into exponent of Z m by R. Okay. Now, please understand that the property, this is the constant, we are defining a constant like Cpg, a constant 4 pi into lambda. So, that Cpg by 4 pi lambda, which is a constant, now it has been designated as Z. So, now, so Z m dot also if you want you can include here, but m dot I have kept separately here because we have to find the mass flow rate of the vapors later. So, Z m dot by R, Z is a constant which combines the properties Cp and lambda. So, now this in minus T infinity into exponent of the same value, but here this is a constant Rs given surface temperature plus the surface temperature So now you can see the boundary conditions here. So when R equal to Rs, when R equal to Rs, I put S here in this R, then you can see that this T infinity, this term will cancel, and Ts will be there. So T will tend to Ts. When R tends to infinity, okay, R tends to infinity, then what happens is, so you can see that R tends to infinity, so this will become exponent of something by 0, something by infinity, so 0, so this will be 1. So when this is 1 and this T infinity minus Ts minus T infinity of this plus Ts, so this and the denominator will cancel, so we will get only T infinity. So you can see that this profile obeys the two boundary conditions what we have. Okay, when you substitute R equal to Rs, you get back Ts. When you substitute R tending to infinity here, you will get the value of T as T infinity. So this is the profile. So when you solve this, it's a exponentially varying profile. As I told you, from this droplet surface, when you draw this, try to draw this. So here this is Ts and this is a T infinity, which is at high temperature here. So you will get a profile which is non-linear and like this. So the temperature profile will be like this. Okay, so this is Ts and this is T infinity. Okay, so this is what we are trying to get here. And now to find the mass evaporation rate, we need the boundary condition at the interface, correct. So you have the droplet surface here, temperature is Ts. So let us see the heat balance. Okay, heat balance at the interface. So this is interface. Okay, now some heat comes through the, some heat coming from the gas phase to the interface, like this. Okay, coming from the gas phase to the interface, some heat that will be taken inside Q I to L, interface to the liquid phase. That way part of this can be used for heating of the liquid. But anyway, this is not going to be with us, because we have already assumed that the droplet is in uniform temperature and there is no heat transfer due to that. So that is one. Then, so now what happens in the absence of that, there will be a mass flow rate of this with its own enthalpy. So liquid enthalpy, okay, HF. Okay, similarly in this gas phase there will be a mass flow rate with the vapor enthalpy, Hg. So now we can write the, so this Qig is written as the conduction term here, conduction term. So for the surface area into K, or the thermal conductivity lambda, into the derivative of the temperature at the interface, okay, at Rs, correct. So this is the Qga term. So this is positive to this. Please understand that negative or negative will be positive. So here the sign is opposite, and that is the direction of the decrease in temperature, but that is inverse to the R, like reverse of the R. So you get a positive sign here, and that will be equal to, this term actually will be equal to m dot, which is going this way, Hg minus m dot Hf, which will be m dot into Hg minus Hf, which is the m dot into Hfg term. So that will balance. So this is going this way and this heat is coming in the opposite direction to the, so this is in the, so this is in the positive R direction and the heat is in negative R direction. But anyway, the magnitude is positive here, so you can get this relationship. So this is the boundary condition at the interface, boundary condition at the interface, correct. So under, when the wet bulb temperature is reached or equilibrium condition is reached, there is no heat transfer from the interface to the liquid phase. This heat transfer is not present. So whatever heat comes from the gas phase, that is Q dot G to I, gas phase to interface, is used only to supply the latent heat of vaporization, that is m dot into Hfg. So this is the boundary condition here. Now you know the temperature profile. Temperature profile is known to you. So now knowing the temperature profile, we can differentiate this profile to get dT by dr, because I need dT by dr in this boundary condition. So I want to evaluate this boundary condition, because by evaluating the boundary condition I can find the m dot. For example, in this itself the m dot is not known to me, correct. So let us assume that when you calculate m dot, we have to use this boundary condition. The assumption made is the liquid temperature is uniform, so Q dot I to L equal to 0. If it is not 0 also, we can make some other add one more term here. For example, If it is not 0, I have to add the appropriate terms to the left hand side. But anyway, to simplify the problem, we have assumed that as 0. So now calculate this dt by dr using this profile. Differentiate this with respect to r and substitute here. Okay. So what we are trying to do here is, in order to get this derivative, I will first differentiate this profile with respect to r. So Tr is differentiated with respect to r. Then whatever r term present in the derivative will be set to Rs. So that I will get the value of the derivative dt by dr at Rs. So that is what we will try to do and substitute here. Once I differentiate it and substitute r equal to Rs, I will put this value, that value here and calculate the value of m dot. So by using derivative at the interface in the expression for the boundary condition at the surface, the mass evaporation rate is got like this. So this is the equation B, which gives the mass evaporation rate. This is calculated from heat transfer. The equation A, on the other hand, here, the equation A here was calculated using the mass transfer. Okay. So you can see this same type of expression is coming, but the property values are different. Say 4 pi lambda by Cpg, Rs is there common, plus natural logarithm of 1 plus a quantity. There also we saw 1 plus By. Here this quantity Cpg into T infinity minus Ts divided by HFG, rate of vaporization. This is called B suffix T, that is the Spalding's transfer number based on heat transfer Bt, which is nothing but Cpg into T infinity minus Ts by HFG. Okay. So that is, see, this is actually a ratio. You can easily understand that this is the heat transfer which is available from the gas phase to the interface, and this is the energy which is required. The HFG represents the energy which is required for evaporation. So this ratio, the available energy for evaporation. So this is the energy which can be fed from the gas phase to this to the interface, and this is energy. HFG represents the energy which is required for evaporation. So this ratio is basically called the transfer number based on heat transfer application. So you get this equation B, which is nothing but 4 pi lambda the thermal conductivity, Rs the instantaneous surface radius of the surface, and by Cpg into natural logarithm of 1 plus Bt. So now please understand that we already got an expression with respect to mass transfer which was 4 pi Rs rho dB. So that is the driving function for the mass transfer is rho into d into natural logarithm 1 plus By. So 4 pi Rs is common. The driving force, the driving property is rho into d in the mass transfer. So 4 pi Rs, the driving force, let us say rho into d into natural logarithm of 1 plus a transfer number B. So By. So y represents the mass fraction of the fuel. So mass transfer based transfer number. So mass evaporation rate is very simple. It is 4 pi Rs into a driving force, which is the property which is driving a particular transport process. The mass transfer rho d is the driving force into natural logarithm of 1 plus transfer number. So this is A. Similarly, you can see here 4 pi Rs, driving force is lambda by Cpg, because heat transfer you have the thermal conductivity as the driving force basically. So this lambda by Cpg into natural logarithm of 1 plus and transfer number. So it is very simple. Evaporation rate will be equal to 4 pi Rs into a driving force, which is nothing but the property involved in the transfer process, which is rho d in the mass transfer, lambda by Cpg in the heat transfer, into natural logarithm of 1 plus a transfer number. So transfer number is appropriately defined for mass transfer and heat transfer. Okay. So for mass transfer, By was defined as Yfs minus Yf infinity divided by 1 minus Yfs. So here Bt for the heat transfer, it is defined as Cpg. So here please understand that in this the physical significance is the difference between the surface mass fraction of the fuel Yfs and that at infinity, that actually represents the gradient. So the gradient of the fuel mass fraction drives the mass there, correct. So that with 1 minus, how much different the surface mass fraction is with respect to 1. So that is the ratio there. In this, as I told you, the energy which is transferred from the ambient divided by the energy which is required for evaporation. So that will be the transfer number. Okay, now, so having two different equations here, but the equation structure is the same, 4 pi Rs into the driving parameter, which is the property which drives the transport process, into natural log of 1 plus a transfer number, correct. However, two equations are there, but here in this equation B, we have considered only the heat transfer. In the equation A, we have considered only the mass transfer, but actually you will see that both should be coupled. So, when you want an equilibrium evaporation or steady state evaporation, correct, equilibrium evaporation or steady state evaporation, the equation A, which is obtained by the mass transfer, should be equal to the equation B, which is obtained by the heat transfer. Okay, because this will ensure that the thermodynamic equilibrium prevails at the VL, that is VLE, that is the liquid vapor interface, there will be thermodynamic equilibrium. So it is called VLE, vapor liquid equilibrium at the interface. So this will be very important. So when, as I told you, there is a unsteady evaporation which is going on initially, but once that condition has reached where the heat is only used from the ambient, which is used only to supply for the latent heat, then we move on to what is called an equilibrium evaporation. Okay. So what is the temperature attained at the equilibrium evaporation condition? So that is what we are trying to find. So for that, one equation is not required. See, for example, now also there is a problem. See, when you use this, how will you determine the Ts? When you use the equation A, how will you determine YFS? So unless these two are combined, we cannot solve the problem. Okay. So as we were mentioning in the mass transfer basics, there we were talking only about YFS, and we told that energy balance is required to find Ts, and from the Ts you can calculate the YFS. But for equilibrium, both should balance. So that is what we are going to do next. Okay. So at a given ambient temperature and mass fraction of the fuel at the interface, that is Ts and YFS, have fixed values at the equilibrium. Okay. And that is basically which is obtained during a steady evaporation process.